All right, hi everyone. Welcome to this monthly webinar on Southwest drought conditions and resources. My name is Curtis Riganti. I'm a climatologist at the National Drought Mitigation Center at the University of Nebraska at Lincoln. I'm also a U.S. Drought Monitor author for both the continental U.S. map, which includes Alaska, Hawaii, and Puerto Rico, and for the U.S. API areas and U.S. Virgin Islands. So for those of you who are familiar with this webinar series, we usually try to keep these briefings to about a half hour. There are casual conversations that'll highlight the current state of drought across the Southwest, and that also highlight some of the great work happening across the region to help build resilience to drought conditions here. These monthly 30-minute briefings began during the 2020 Southwest Drought as part of the Southwest Drought Learning Network's drought monitoring and reporting team, and will continue as long as there are areas of extreme and/or exceptional drought conditions in the Southwest United States. I'd like to acknowledge Emily Elias, the director of the USDA Southwest Climate Hub, and Joel Lisenby from NOAA's National Integrated Drought Information System as primary co-organizers of these webinars. The Drought Learning Network aims to support peer-to-peer learning by linking climate service providers with resource managers and resource managers with one another to increase landscape and community resilience in current and future drought. To begin, I'd like to acknowledge that the land each of us is on today is the ancestral land of tribal and indigenous cultures, and I'll pay my respect to their elders and chiefs, both past and present. I welcome all tribal and indigenous peoples who are joining this webinar today. Before we get started, let's cover some logistics. So for the webinar, everyone will be muted and the webinar is being recorded. The webinar recording will be available in a few days from the NIDIS YouTube channel and at drought.gov/webinars. The format of today's webinar will be a presentation by each of our invited experts, followed by a time for questions. If you would like to ask a question, you may do so at any time by typing your question into the questions box. Following the three presentations, the questions will be moderated by Joel Lisenby, the Intermountain West Drought Early Warning System Coordinator at NOAA's National Integrated Drought Early Warning System. So with that, I'd like to welcome and introduce today's speakers. First, Dr. John Myers, a research climatologist with the Utah Climate Center and Utah State University. John specializes in numerical modeling for both weather and climate timescales, and he currently oversees the Utah Climate Center's operational forecasting model platforms. John is also the state coordinator for COCO-RAS and serves as part of the Utah Drought Task Force. And then Dr. Simon Wong studies climate variability, weather processes, extreme events, and climate prediction. He edited the first AGU monograph on climate extremes, which was published in 2017. He has led the research and development at the Utah Climate Center and is an advocate for climate services. So with that, take it away.
Thanks, Curtis. Awesome. Well, hello, everybody, and I appreciate the opportunity to speak to the collective group here on the Southwest Drought Update. My name is John from the Utah Climate Center, and I'll be guiding you through our current conditions and some expected outlooks going forward. We'll start off with the current drought classification, which has seen quite a bit of improvements as a reflection of the positive monsoon season that we have seen. Yeah, so the current drought classification reflects the positive monsoon season, and the majority of the significant drought classification is residing in Nevada and Utah, with a few pockets in northeastern Colorado and eastern New Mexico. Arizona, New Mexico, and Colorado have these almost unfamiliar colors of white and yellow, showing we've had some significant improvements over the last 3 to 6 months, again, as a reflection of the monsoon season and the summer rainfalls. Some of the drought changes that we have seen over the last 3 months are reflected in this map here, and we can see the vast majority of the region is exhibiting green color scales representing class improvements, where some areas, specifically in New Mexico and Colorado, have seen upwards of 3 class improvements over the last 3 months. So again, this is a very significant improvement for most of the region, reflecting the monsoon season's summer rainfall pattern. However, the northern latitudes, which is going to be somewhat the theme going forward, has not benefited as much, and therefore over the last 3 months, most of the northern latitudes of our southwest region have experienced either no change or a few pockets of 1-class degradation or 1-class improvement. We'll focus in on our current conditions, looking at temperatures over the last stretch of time. This is going to toggle back and forth between the last 3 months, which is what we're looking at right now, to the last 12 months. So we can now see sort of the water year perspective. And this is going to give us some idea of how our summer has been. So we're toggling back and forth between the temperature departure from normal here, showing most areas in the warmer than normal conditions, and then the percentile there, showing most areas are experiencing top 33 percentile, top 10 percentile in the orange, or record warmest in sort of that burnt orange color across the northern latitudes. And so the northern latitudes are, again, where we've seen the most amount of drought pressure over the last 3 months during the monsoon season, and is not too unexpected given what the monsoon has done and how that system generally works. Expanding across the water year, so looking back into last October, over the last 12 months, we can now compare and see how the conditions across the region have changed. Temperatures, the overall region over the last year was warm, not nearly as warm as the last 3 months, but over the 12-month period, the desert Southwest was above normal. Most of the areas experiencing top 33 percentile, and a few small pockets in the top 10 percentile relative to the long-term average. So again, and this has been sort of the case over the last few years, the summer months have been warmer than normal, and some areas across the entire year have been quite a bit above normal compared to the long-term average. Focusing on precipitation now, this will be a similar style of slide where we'll first focus on the last 3 months here, toggling back and forth between the percent of normal and the departure and percentile. And you can see lots of greens on this, which is amazing, reflecting the fact that the monsoon was very active and widespread. So normally our season can be either influenced by the monsoon or a non-soon, if we want to use that term, where we don't get any precipitation. The monsoon season can funnel precipitation in one area but not the other, or we can have what we did this year, where the monsoon is pretty giving across the entire region. And it sort of wobbles back and forth, and we see widespread above average precipitation, and some areas experiencing near record precipitation over the last 3 months. So this is exactly what we really want to have happen during the summer months, when if we were to miss out on the monsoon, we can certainly exacerbate drought conditions. So this is really excellent to see for a summer wrap up on how the monsoon season played out. Now, extending our perspective into the last 12 months, our 2022 water year on the right shows that despite the active monsoon season, the underperforming snowpack and spring conditions are translating to a year perspective that is either near normal to below normal for just about everywhere. A few pockets in Arizona and New Mexico flipped their switch to above normal precipitation for that water year. And that's mostly a reflection of just the insane monsoon season that we have seen so far. So again, sort of a tale of two time scales here. Monsoon season, excellent. Water year, a little bit less optimistic in terms of water resources across the region. But we'll certainly take what the monsoons delivered this year and hope to carry that trend forward. Standardized precipitation index is a nice way of looking at precipitation in a statistical context for that time of year, that window. On the left here, we'll be looking at 90 days. So again, sort of the monsoon season's perspective, and you can see just about everywhere is dominated by these greens and blues. There's a few pockets of oranges and yellows, and then a lot of gray area there. So again, just reiterating the fact that the monsoon season was quite a bit above normal and was very widespread in that sense, which is about of an ideal of a monsoon season as we could ask for. Extending that back across the water year here, we are looking at the 12-month SPIs, and again reflecting the fact that despite the short-term meteorological improvements from the monsoon season, the long-term hydrologic drought still remains a significant problem in the region. We've traded in all those greens and blues for oranges and yellows, and so just about everywhere in the region is experiencing some sort of at best near normal and at worst quite a bit below normal precipitation over the last 12 months. So again, a tale of two time scales that we're looking at for drought considerations throughout the desert Southwest. So it's been hot, but it has been pretty rainy. So looking at evaporative demand over the recent conditions, we're looking at evaporative demand drought index, or EDDI, on the left over the last week. And this is a story that's played out pretty much since the end of July for the region, thanks to the activity of the monsoon season, which has kept things cloudy and rainy. Our evaporative demand across the entire season has been pretty minimal, and that continues to be sort of the theme heading into early fall season. So that's great news. The soil moisture that we have in place, thanks to the monsoon season, which we'll talk about shortly, is not really being demanded on by the atmospheric conditions of wind and humidities and temperatures. So that's great. Another perspective on the right is the evaporative stress index, which is a little bit different context of evaporative demand on the surface. This one looking a little bit more at evapotranspiration and a vegetation type of perspective. And that shows, again, this north to south split as a function of just how far reaching the monsoon precipitation surges went throughout the overall season. And again, the northern latitudes exhibiting far more evaporative stress than the southern latitudes. So depending on where you're at, there's some good news and some bad news based on the evaporative demand on the land surface at the moment. Soil moisture year over year has had some noticeable improvements versus this time last year. We have had two back-to-back pretty good monsoon years, but this year really has benefited the soil moisture. And we see most basins across the region are near normal to above normal soil moisture, which is excellent, just what the doctor ordered heading into our early snow accumulation season for the high terrain that we'll see beginning to descend over the next couple of months. So this is a shallow soil moisture perspective here from NRCS looking at snowtail and scan stations. And they show the shallow soil moisture reflecting the highly beneficial monsoonal precipitation. I will note that the deeper you go, the more dire it gets in terms of soil moisture conditions, again reflecting this short-term versus long-term drought pressure that the region has experienced. This will show a satellite perspective, so remote sensed soil moisture conditions. This is toggling over the root zone soil moisture at the top down to the shallow groundwater. And then again up here we'll recycle to the surface soil. So this is sort of giving a top-down perspective, and you can see the deeper you go, the more red and oranges populate this map, representing the significant stress that our groundwater aquifers and the long-term hydrologic drought has placed on the region. But beneficial short-term monsoon conditions have upped our shallow soil moisture conditions. Using the NASA SPORT model to track soil moisture changes, this is showing 1 month difference in the total column relative soil moisture. So, and this is up to date as of this morning, and we can see the region primarily has experienced 1 month improvements to soil moisture, so that wet monsoon has continued into early fall in terms of providing ample soil moisture conditions. But we are now beginning to see, if we looked at this on a shorter time scale, the reflection of the recent dry and warm weather beginning to sort of flip the switch, and we're now beginning to trend a little bit drier for our soil moistures across the region. But the fact that we have upward trends over the last month shows that we are holding on to as much soil moisture as we possibly can through the transition season. This figure here will toggle over year-over-year changes from the GRACE satellite, so we can see what last year's beginning of the water year versus this year's beginning of the water year. And we can see the region still exists under pretty significant groundwater pressure from the drought perspective. Those significant areas have toggled a little bit away from the western US and a little bit more to the eastern southwestern states, Colorado and New Mexico. But again, the region as a whole continues to exhibit lots of significant groundwater and hydrologic levels of drought stress. All right, reservoir capacity, which is probably the best barometer for our hydrologic drought conditions, is shown here throughout the desert Southwest region. Major reservoirs are plotted based on their capacity. So the big dots are the big reservoirs, Meade and Powell. And we can see those are demonstrating the ongoing significant pressure, far less than 50% of capacity for those two big boys. But region-wide, a lot of the middle-sized and small-sized reservoirs are also experiencing problems with their capacity, again, reflecting this is year 3 of significant drought throughout the region. So we continue to draw down our savings account in those reservoirs to try and get us through each year. Lake Powell now sits at 24% capacity, Lake Meade at 27%, and we can see the long-term drawdown of Lake Powell since the beginning of 2000. We have the long-term cycles in the climates, but overall each down cycle is drawing us down to lower and lower levels. So again, Lake Powell right now is at a pretty low point, historically speaking, at 24%, and we're dropping about 1% every month or two. And so this is something that water managers are absolutely keeping a very close ear on in terms of those reservoir capacities. All right, looking forward, the CPC has been tracking the expectation for the last couple of months for this rare triple dip of La Nina. So back-to-back years experiencing La Nina type of conditions. This year, thankfully, is expected to be a weaker version of La Nina. However, the La Nina conditions tend to push the desert Southwest towards mild and dry winters, and that extends up through the southern latitudes of Utah and Colorado. And so we can see the October through December or fall and early winter months projecting to hold on to that La Nina type of pattern, with temperatures expected to be above normal and precipitation expected to be below normal. So to summarize, active and widespread monsoon has really improved the short-term drought conditions in the region, and we've seen the beneficial improvements in the drought categories, with some areas seeing 2 to 3 categories of improvements over the last few months. So that's really a status quo for the region's long-term drought concerns. The monsoon helps, kicks the can down the road a little bit, however, it doesn't move the needle much for our long-term hydrologic concerns. But however, the monsoon really didn't exacerbate in a time where we can certainly, if we get a monsoon, take things to another level of dangerous drought. So positives as we start our 2023 water year, we've had pretty limited evaporative demand starting our fall transition season, and that's led to high amounts of soil moisture. And the expectation there is the high soil moisture, should it be locked in over the next couple of months, will translate to a high spring stream flow efficiency, meaning that what melts is likely to make it down the river systems versus going into the soils. And also winter agriculture across the region has had a lot of relaxation in the drought pressures. I've heard lots of good news from farmers and ranchers throughout at least Utah that their expectations are positive for their winter crops. So that is great news, and again, a reflection of the last few months of conditions. However, negatives looking forward is the expectation for our 3rd year of underperforming expectations for our winter season snowpack, which is where we get most of our water supply from. So that's certainly not a positive as we look forward to the start of that season. And the snowpack outlook is unlikely to begin any meaningful drought improvements, even if we have a near normal type of year, which would be probably one of the better case scenarios. We're going to need some well above normal type of conditions in the snowpack. And so the outlook right now is one that makes us hedge our bets towards not much meaningful drought improvements to groundwater and reservoirs next year. I will caveat that with there are lots of scenarios still to play out over the next 6 months. So it's really difficult to pinpoint the end result, but right now My bets are on lowered expectations for our winter snowpack and not much meaningful drought improvements next spring and summer. So that's what I have, and looks like we'll hold off on questions till after Dr. Wong's presentation. So thank you very much.
Thank you for your presentation.
Thanks, Joe. Hello, everyone. The next 10 minutes will be for me, Simon Wong, introducing a study collaborating with NIDIS, with Joe as well. Because of my my lingering cough from COVID 3 weeks ago, I will be presenting through a pre-recorded video. So you're seeing this is just published on using Twitter data with machine learning approaches to see if social media information can be used to improve drought depiction and also drought prediction over sparsely populated regions. And the presentation will start with me introducing the general ideas for about 3 minutes. And then we have Sabaji, the first author here, who was a PhD in computer science, working on talking about the details about his research. So Joe, please play it.
Hello. Today, I'd like to first introduce some backgrounds on why we want to pursue the social media route of drought information. In Utah, the drought situation has two important issues. The first one is a decadal drought cycle, which is quite strong. The other one is the lack of data. This map is the population density, and you can see how sparse the observations can be because they correlate with human population. We try to establish as many stations as possible, and there's still a lot of gaps to fill. So we collect the social media data, such as Twitter. With those tweets, we create an initial sentiment analysis that give each tweet a positive and negative score. And then we found out that people in Utah don't really tweet about drought. So we don't really find much information that can build enough realizations. And it turns out that Utah is among the states that don't really have a good correlation between drought and tweets about drought. So we try to be proactive. We engage in news media, public radio, and also local TV stations to encourage citizens to tweet about droughts. In the meantime, we have to seek data from Colorado to analyze and build our sentiment analysis model. This is what the negative sentiment tweets looks like with the various of filter. This is the ratio of negative and positive sentiments. And then you can start to compare with how the drought in Colorado has evolved. We also found a different category of drought calculated from the GRACE satellite, which detect the micro change in gravity and then detect water storage changes. Through the second line, you can see that the ratio between positive and negative tweets and the groundwater drought, they have some sort of relationship. First of all, they seem to be inversely correlated, but this is not possible because groundwater status takes time to react to weather conditions. But if you look at the data again, and it could be that there's a phase shift. If that's the case, it would really mean something because a phase shift means that if you monitor the rate of change of tweets or sentiment of the tweets, and it's likely that you can predict groundwater drought status from a week to several weeks ahead.
So the goal of this study is to analyze social media data in conjunction with the meteorological records to see if we could understand the progression of drought. So to capture those things, we searched for keywords such as stream flow, drought, less water, crops, farmers, dried, like a variety of terms. So this is just a basic subset. Twitter lets us access its data using two different APIs. One is the standard API and one is the premium API. The standard is basically free, but you can only get access to real-time data for the past 30 days. On the other hand, there is a premium API, which is a paid service through which you can get access to historical data and also gather tweets regarding a particular location. So we faced challenges, and hence we decided to move to Colorado, where we saw a lot of tweets coming in that had associations with drought. And for the 2021, the data collection period was between January to April. But not all of these tweets were depicting drought. So first you collect the data, then you clean those data, and then you pass it through a prediction model. And then finally, you evaluate against some real outcomes of the tweets based upon some chosen evaluation matrix. So first, Twitter user referred to drought in a variety of contexts, from referring to traditional climate change to trophy drought or playoff drought in the context of sporting events or so on. So we had to clean those. The final count of the tweets after data cleaning was 25,597. Our goal was to clean tweets as much as we can. It was a lot of manual labor, and the more manual labor you give in, the better the machine learning models are. So just an overview of what did people tweet about in 2019. So you can see these are some of the common terms that they had used, like Colorado, drought monitor, state, drought, year. Similarly in 2020. So to analyze these types of differences, we used a sentiment analysis using lexicons. So we used a Python library to read in the sentiment language resource. So basically what it does is you pass a sentence to this library. It first tokenizes and breaks those sentences and tags relevant part of speech associated to it, a tuple of numerical values, like how much positive or how much negative, like from 0 to 1. So here are some examples of some sample positive and negative tweets. So for experimental setups, we chose generalized 3 different machine learning models: generalized linear model, support vector machine, and deep learning framework. And then we separated out 40% of the data for testing. Along with that, we also performed a 10-fold cross-validation to remove any bias in our trained models. Machine learning models take a lot of time and a lot of experiments with different features, how much features we need to add. So for our training data, we used data from 2019 and 2020 and left the 2021 data as our unseen data, which we would use later for our validation or testing. So in order to start our experiments, we had to design a baseline model. So this control run model had 2 different goals. So first is to show what percentage of the observed variation in the PDSI value of the current week can be explained by the variation of the meteorological variables over the past 3 weeks and the current week. The focus was how we could use this control run, add Twitter data on top of it, and see how much improvement we can get. So these are the results of the control run. You can see the RMAC and the correlation. So the lower the RMAC, the better it is. The higher the correlation, the better it is. So basically, the x-axis are my true PDSI values, and the y-axis are my predicted PDSI values. The closer the blue dots are to the red line, which is basically my reference line. So the closer these blue dots are towards the red line, the better the performance of the model is. Remember, we told the generalized linear model had the greatest correlation. Similarly, you can see here. So next, we wanted to add, as I was telling you, Twitter data to a control run D. Social media data basically was added in the count of the positive and negative tweets per week. So you can see model 1, which is our control run denoted by D. Model 2 was D plus N and D plus P plus N. In this way, you can see P means the number of positive tweets for the current week. N means the number of negative tweets for the current week. 1N means number of negative tweets 1 week before. 2N means number of negative tweets 2 weeks before. Similarly, for positive tweets, 1P and 2P. Here we can have a visualization of how our Twitter-based models performed against our control run. The x-axis is basically the root mean square error difference with respect to the control run, and my y-axis is the correlation difference with respect to the control run. This point here is basically where the performance of the Twitter model is equal to the performance of the control run. So you can see here, most of these models, we discussed about model 10 and model 6, performed better in case of generalized linear model. In order to measure the improvement, these hollow circles are basically our control run model, and my filled circles are basically the Twitter models. X-axis is my R squared difference, and my y-axis is RMAC, root mean square, A performs better than B if it has a lower RMSE and a higher correlation. So you can see in most of these cases for model 1 deep learning, we had model 4 performing better than model 1, here model 10. So this will give you a better visualization. So the fact that all the arrows are pointing to the bottom right means that model 10 indeed outperforms the control run model in each of these cases. So moving forward, we also wanted to see how population densities or land use might affect the trained Twitter model. So moving forward, what we want to do is build a prototype model where given the Twitter data that we can obtain, we want to predict the future PDSI values in advance. We want to have a predictive analysis. That's the forward or future goal of this project. Thank you.
So I'd like to really thank Joe to provide feedbacks. This project couldn't have been successful without Sabaji, who is a computer scientist, and also Hongping, who is a climate modeler. And I very much thank Nidus for providing support. Thank you.
Great. Thank you, Simon. I'm sorry that you're still lingering with COVID, but that pre-recorded video was great. We've got some questions now for both John and for Simon. And we have about 6 minutes for questions. So when I ask you a question, if you could try to keep them a little bit short. The first one, going back to John's presentation. John, we've had 2 great monsoons in a row. We've also had 2 La Nina years in a row. Are those 2 events related?
Great question. One that we get often, the connection between the El Nino, La Ninas in the summer. And
Thanks,
there has
Joe,
been
thanks,
about
everyone.
15 to 20 years of people trying to
questions.
find the relationships between the ENSO pattern in the Pacific and our summer precipitation. And it's fallen mostly to the wayside, and there really hasn't been any statistical or physical connections between the Pacific and our summer seasons. The monsoon season is highly variable. It can be all over the place depending on lots of different factors. It's a very difficult seasonal pattern to predict on the climate timescales. Even the weather forecasters struggle on the daily timescales. So as far as we know, there isn't any linkage directly between El Nino, La Nina patterns and our summer monsoon. We've just been pretty lucky the last couple of years. If we think back, the start of our significant drought in the region came apart when we got the monsoon back in 2020, I think it was, where we just didn't get any summer monsoon rainfalls. And that was really the catalyst for driving us into the D3, D4 categories. 2 years of good monsoon seasons haven't been enough to offset the La Nina pressures on the snowpack throughout the region. And so the resulting effect is ongoing significant drought throughout the region, certainly from the long-term perspective.
Got it. Thanks for that. So it sounds like, well, we don't really know about the connection between the drought and monsoon, but don't get too excited for the 2 monsoons because we still have to wait to see what winter looks like, because that's really where our rain's coming from. That's what I'm hearing from you.
Exactly.
Thank you very much for that, John. I had one question come in asking if Simon's video would be made available. So this whole webinar is being recorded, including Simon's video will be embedded within that. And that will be on drought.gov/webinars. Whenever I get around to it, it'll probably be later this week. So be watching for that. Thanks for that question. And also a reminder, if anybody has a question for either John or Simon, go ahead and plop it into the questions box. And if we have time, we'll get to it. We've got just a few minutes left. Simon, one question for you, and that is, so you said that Utahns don't tweet that much, but you got enough tweets from Colorado. I know that this study is wrapped up and you published this paper, but is it still important to encourage people to tweet to help your model to get enough data going forward?
Yes. After we launched that media campaign, we did see about half a month through 2 months later that is an increase of tweets. And we don't really know if that's really the effect of the media campaign, or it's just the fact that the drought has worsened. Could be the combination of the two. But we don't have any explanation on why there's a geographical differences in terms of how people tweet about weather phenomena and drought. But yes, now the more we get from tweets about drought, the more specific the tweets content, what kind of drought they're referring to, the more powerful that the machine learning algorithms can pick up those slight sentiment. It's really the sentiment, not a frequency of the tweets that can be used to depict the drought more accurately or predict the drought.
Okay, so just building on that, if it's the sentiment that you're really looking at, it wouldn't really matter if people posted pictures on Twitter because the model's not picking up on the pictures. It's really the words that people are using. Is that correct?
It's only confined to, excuse me, it's only confined to the methodology we use. Now we use lexicon, which only detects text. So if the person posts a drying field picture, but then he described it, saying, "Oh, my field is drying up," and then the lexicon will pick up the text and reflect that sentiment. Later on, if people randomly or systematically take pictures without referring to the drought status, it of course has to use a different, more like a image processing methodology to pick that up. But it seems it seems interesting. We've been thinking about there has been many video cams, like the Department of Transportation has a lot of the videos, and also some webcams that look at the vast plains area in Colorado or in Nebraska, in the Central Plains area. So maybe those can be used to detect something. I have seen some programmers presenting in the American Meteorological Society back in 2019, talking about how they use traffic camera to predict fog and visibility changes. I think there's some possibility there we can try.
Oh, great idea. Simon, about 2 months ago, we had Dawn Browning on this webinar series. She was talking about using the PhenoCam network to detect drought. I'd encourage you to go back and look at that webinar, and I'm happy to make that connection for you too. That's all the time we have. A huge thank you both to John and to Simon for sharing your time and your expertise with us today. Our next webinar will be in early November. We haven't pinned down an exact date for it yet, but be watching for your email for the next one. Also, thank you for Curtis for kicking off this webinar today. Curtis, do you want to say anything before we wrap up, or are you good?
I'm good. Thanks for letting me lead this.
Sure.
Really good
Thanks,
presentation.
everyone.
Yeah.
Bye.
Thanks, John, Curtis. Thanks, everyone.
Thank you.